Okay, let's continue with the wave equation. We solved wave equation under some assumptions, and we used the product method, right? Just like what we did for the potential equation. Now, sometimes we can write down equation slightly in terms of the initial data. That's a different approach. So maybe it's good to start with an exercise. I want you to try to do it. So we had the wave equation, which says the second derivative of u with respect to x is equal to a constant 1 over c squared, second derivative of u with respect to time t. It is for some string which goes, say, from x equal to 0 to x equals a. So this equation is an equation for a function u, which depends on x, space, and time t. Right? Now let's introduce two new variables. Let's call one of them z, let's call the other one w. Let's say c is x plus ct, and the other one, let's take it x minus ct. There are two things I want to think about. If I define a new function, I would show that with v of, say, z and w. If I define this function, if I define v of zw to be equal to u of x and y, one, I want you to write the equation, the wave equation, but for v. Plug in somehow v into the equation and see what the equation would be for this function v in terms of z and w, rather than, sorry, it is x and t, not x and y, rather than x and t. That's one thing. Two, well, it's not really a mathematics type of question, but it's nice to think about, because we said this equation describes the vibration of string. You can think about it yourself. X is something which shows you the location. T is something which shows you time, right? Defining z as x plus ct, where c is a constant, in the first glance, it might look, though, as we are adding something which is kind of, its unit is something like meter, it's about the location, distance, with something which measures time, right? And its unit would be something like seconds. Does adding these two things make sense? I mean, you usually add 2 meters plus another 2 meters, right? It would be 4 meters. You wouldn't say what is the sum of 2 meters and 2 seconds. So it's not a math question, but it's nice to think about it. Does this sum here really make sense? This is a meta math question. But the more important question for me is that here we have an equation for u, and we have a relation between u and v, and how x and t are related to z and w. I want you to spend some time right now to write down, to transfer the equation for an equation for v in terms of z and w. This is a very doable practice. So think about this for a few minutes. Yeah,
How to
sure.
approach it, I don't know.
Yeah.
So those equations, you gave us c equals something and w equals something.
Yes.
Can we just plug in those for each value? So for like x, we can use z and square that, and then simplify it.
No, that is
Or
not. No, that's not true. So if you,
I'm just trying to think of something because I tried other things and
I see. So the idea. Okay, let me start right. So the idea is to use a theorem which you've seen in calculus, is the chain rule. So let me write down the equation again here. This is our equation. And then we define z to be x plus ct, w to be x minus ct. And then we defined v of z and w, these new variables, to be u of x and t. Now, in order to find the equation for v, we can use the chain rule. So let's remember, what does the chain rule say? So this is the multivariable version of the chain rule. Probably you've seen it in Calc, I think 3 or 4. Let's see.
What is it? Is it like the derivative of the first times the second and then plus the derivative of the
Yes.
second times? Yeah.
Yeah, exactly. So that is correct. Yeah. Also what Thomas is saying is correct. So chain rule here tells us that if we want to take derivative of u with respect to x, what we can do is we can take derivative of v with respect to w and multiply that derivative of w by multiply that by derivative of w with respect to x. Or, which it means we can add this to, we can take derivative of v with respect to z and multiply that by derivative of z with respect to x. Okay, that's what chain rule tells us.
Got it.
And then,
All right,
great, yeah. Okay, I would continue this computation now. So also chain rule tells us that derivative of u with respect to t is equal to derivative of v with respect to w times derivative of w with respect to t plus derivative of v with respect to z times derivative of z with respect to derivative of t. Now let's see if we can, what we can do with these things. So the main point here is that we know these things. So look at this thing, this z equals x plus ct. So derivative of z with respect to x, it means assuming x is the variable, if we take derivative, we would just get 1. The coefficient of x is 1. And if we take derivative of z with respect to t, if you take derivative with respect to t, the result would be just a constant c. For w, if we take derivative of w with respect to x, we would get again 1. And derivative of w with respect to t, we would get minus c. And we can plug these things into our equation. So here, derivative of w with respect to x, it would be 1. Z with respect to x would be 1. W with respect to t would be minus c. And z with respect to t would be plus c. Right? So it would be just derivative of v with respect to w plus derivative of v with respect to z. The other one would be c. We can factor c, derivative of z with respect to z, derivative of v with respect to z, minus derivative of v with respect to w. So, but the point is that in our equation, in our wave equation, we have the second derivative. So we should do this one more time. So let's do that. I would go to the next page. I would rewrite the final thing we got. We learned derivative of u with respect to x is equal to derivative of v with respect to z plus derivative of v with respect to w. That was one equation. The other equation was derivative of u with respect to t is equal to constant c times derivative of v with respect to z minus derivative of v with respect to w. Okay, now we need to apply this chain rule one more time. So again, let's apply the chain rule. I had told you that the integration by part is one of the most important things in math. Chain rule is also up there. These two things are both very important. It's very good to be able to use both pretty well. So the second derivative of u with respect to x would be, well, again, we should do that. We should take the derivative with respect to x of the first term, which is derivative of v with respect to z, plus we should take derivative with respect to x of the second term, derivative of v with respect to w, right? Now, again, we can commute these things. So suppose here, derivative with respect to x commutes with derivative with respect to z. So it would be derivative with respect to z of derivative of v with respect to x. So I change the order of derivative with respect to x and derivative with respect to z. Let's do the same thing here. Let's suppose we can change these two derivatives. Suppose they commute. So we get derivative with respect to w of derivative of v with respect to x. Now we can do the chain rule. So derivative of v with respect to x would be derivative of v with respect to z times derivative of z with respect to x plus derivative of v with respect to w times derivative of w with respect to x. We use the chain rule here. Now we have derivative with respect to w of derivative of v with respect to x. Again, derivative of v with respect to x is the same thing as before. So we just write down that, whatever that is. So derivative of z with respect to x was 1. Derivative of w with respect to x was 1. So I would just write 1 here and 1 here. So if we apply now derivative with respect to z to this thing, we get second derivative of v with respect to z plus. We should apply this derivative with respect to z to the second term. You would get second derivative of v with respect to z and w plus, if we apply this derivative with respect to w to derivative of v with respect to z, we get second derivative of z with respect to w and z plus, then there is another term, second derivative of v with respect to w. Now, again, as I told you, we assume that derivatives commute. So these two terms are the same. Doesn't matter here if we first take derivative with respect to z and w, or first we take derivative with respect to w and z. So these are equal, and they're equal to 2 times, well, one of them. They're the same. Right? So we get second derivative of v with respect to z plus second derivative of v with respect to w plus 2 times derivative of v with respect to w with respect to z. So where did we start? This was our starting point. Second derivative of u with respect to x, and this is our ending point. This is the final point. So let's write these things next to each other. It means second derivative of u with respect to x is equal to this thing. Okay, any question in these computations about chain rule and just commuting the derivatives? Everything's good? Okay, great. So let's see. Let's continue. So yeah, that is true. So that's the course is about partial differential equations. So these are partial differentials. So of course there are so many partial derivatives. That's the main topic, right? So now we can go and try to compute the second derivative of u with respect to t squared. So I wouldn't compute that. It would be very similar to the previous thing. There would be just some constant c. So if you, let's go back. So if you remember, this other one had some constants c here. When we do the chain rule again, we would get another one of these actually. And the final result, if we do exactly the same computation, the final result would be something like this. It would be c squared. Let me see. Second derivative of v with respect to z plus second derivative of v with respect to w minus 2 times second derivative of v z w. So I'm not repeating that. It's just completely similar to the thing we had in the previous page. So in the previous page, we computed second derivative of u with respect to x is equal to second derivative of v with respect to z plus second derivative of v with respect to w plus 2 times the second derivative of u with respect to z and w. So we have these two expressions. Now the wave equation tells us that second derivative of u with respect to x is equal to 1 over c squared second derivative of u with respect to t. Now, if we plug in these things into this equation, the second derivative with respect to x is what we have here. So it would be second derivative of v with respect to z. So I would just write that. Equals 1 over c squared, which comes from here, times what we have here, but we have c squared times something, so they cancel each other. We would just get 1. And what do we have? Well, we have this. Okay. Therefore, the left-hand side is equal to the right-hand side. These two things are equal. Now, the interesting thing is this thing here is equal to this one. So we can cancel them from both sides of the equation. Great. Great. This thing here is equal to this one. So we can cancel that from both sides of the equation. And these two things are equal, but negative of each other. So I would take 1 to the other side, and I would get 4 times second derivative of v, derivative with respect to z, derivative with respect to w is equal to 0. Therefore, you have this equation. So second derivative of v with respect to z with respect to x is equal to 0. So this is wave equation for v in this new coordinates. So the wave equation becomes second derivative of v, zw is equal to 0. So rather than finding u, we can find v, and then through the relation we had between u and v, we can translate that back to you. Of course, this equation looks a lot easier to solve, right? It's a very neat equation, right? It looks, well, at least it looks better, and we will see it's easier to solve. Any question about the process, how we got here? Okay. So this kind of change of coordinate was a great thing to do, and there's a little bit math intuition, also physics intuition behind that. No, the substitution doesn't come from trial and error. There is a very interesting type of intuition behind that. It's a little bit out of the scope of the thing we are talking about now, but the question I asked you, that does this sum make sense? I said you might think this sum doesn't make sense because this is x and its unit, this is location, for example. It has the unit of x would be, if you think in terms of physics, would be different with the unit of t, which is time, like adding 2 miles to 2 minutes, right? 2 seconds. That doesn't make sense. But here there's a reason why this quantity makes sense, and it's interesting to look at that. If you answer to that question first, then you would understand why this makes sense. And the answer to that question is that C here has some meaning. Exactly. So C is something you are familiar with, actually. There's a reason why. Yeah, your guess is correct. So I don't want to explain that now. I think it would be interesting for you to think about. But then if you understand that, that kind of would make sense why this substitution is something good to do. That's an intuition. But anyway, that's a little bit out of the scope of the things I'm talking about now. So, so we have this second derivative of v with respect to z, and w is equal to 0. This can be written, we can write the second derivative as derivative with respect to, say, z. Well, let's take w out. I have derivative v with respect to z is equal to 0. Right? So whatever this thing is, its derivative with respect to w is 0. So this part does not contain any w, right? Its derivative with respect to w is 0. So it does not contain any term which has w in it. So this thing can only be constant, or it might have z. So however, it might have z. So this partial derivative of v with respect to z is a function of z. Okay? So it's a function of z. Let's use a notation for that. Let's use, I don't know, let's use f1. It's f1 of z. Any question up to this point? Is everything clear? Great. So derivative of v with respect to z is a function of z. We denote that by f1 of z. Now, if we have this, we can kind of integrate that to find v. So integrate with respect to z to find the function v, right? So if we do that, kind of derivative with respect to z and integral with respect to z, they cancel each other almost. So we would get v is equal to integral f1 of z dz plus a constant, but it's constant when we are thinking about z to be the variable. This constant might have w. It's constant with respect to z. So the constant part might still have w in it. So that would be either a constant or a function of w. So let's show that with f2 of w, right? Because if you kind of go back, if you take derivative with respect to z to go back, v would go to derivative of v with respect to z. If you take derivative with respect to z, this one would go to f1 of z, and this one, because it doesn't have any z, it would be 0, right? So this makes sense. Great. So now in some sense we have v, right? V of z and w is equal to integral of f1 z dz. This is a part which depends on z plus f2w. And that's great because we had tried this once and it didn't work in the problem we tried. Do you remember once we were trying to solve a PDE and I said, maybe if we can write down the solution as a sum of a part which is just depends on one variable plus another part which only depends on the other variable, we can solve the equation. But it didn't work. But here it does. You see v, which satisfies the kind of modified wave equation, can be written as one part, which is a function of z, plus another part, which is just a function of w. They're not mixed. And that's great. But now we want to go back to the function u. Really what we were looking for was u. It was not v, right? The original equation was an equation for u, right? We were trying to solve this one. But that's not hard. Well, I mean, we remember that u of x and y is equal to v of z and w. So if u of x and y is equal to v of z and w, and well, I also know what z is. Z is equal to x plus ct, and w is x minus ct. Well, we can now compute this thing because v is equal to integral f1 z dz plus f2w. I can just plug in z and w with the things we have here. So let's do something. So this thing here, this thing in the blue box is only a function of z. Let's denote that with f1z with capital F1, right? Let's define capital F1 by this notation, because whatever this integral is, it's a function of z. Note that the z in dz is a dummy variable. It's not like we're integrating over z and getting rid of that. That part is something with variable z. So it is f1z plus f2w. Now, if we write down what z and w is, it is f1 of x plus ct plus f2 of x minus ct, right? Therefore, u of x and y is equal to f1 x plus ct plus f2 of x minus ct, right? So we are almost kind of done. Everything is almost clear now. There are just some, in order to really understand everything and finalize our thing, we can just look at the boundary value condition. So let's look at the boundary value condition. We had boundary value condition and we had the initial condition, right? So what was so boundary value and initial condition? Let's write them. Okay. We kind of so let's see. So what was the initial condition? The initial condition was what was the initial condition when we were studying the wave equation? So u at every point x at any time 0 at the time 0 was given by a function f of x, right? The initial condition was like that. But if you remember, the initial condition has also a second part. I told you if they tell us in the time t equals 0 the string looks like this, this is not enough to understand what would be how the string is going to move, because the string maybe is going to continue its movement, maybe it's going back down, maybe it's going the other direction. We don't know that. So we also need to know what is derivative of u with respect to x at time t equal to, sorry, derivative of u with respect to t. We want to see how it's moved. So we need its velocity with respect to t at time equals 0, right? So suppose these two things are given as the initial part of the data, as the initial equation. Now, we know what is u of x and y. So u, sorry, u of x and y was equal to, is equal to f1, sorry, not x and y, x and t. We have so many variables. f1 of x plus ct plus f2 of x minus ct. So for the initial condition, we are assuming t is 0. So let t to be 0. So u of x and 0 would be equal to f1 of x plus f2 of x. On the other hand, so this would be one boundary condition. So let's call this one boundary value condition number 1, which corresponds to this thing here inside the red box. But there is another one, the second boundary value condition. I want to compute that one too. In order to compute that one, I should take derivative of x with respect, derivative of u with respect to t. Derivative of u with respect to t would be derivative of this guy with respect to t. Well, as you can see, there is some constant c here. It comes out. So we get c derivative of f with respect to t. We would show that f1 prime at the time t equals 0, which would be just x plus 0. Plus, sorry, minus, again, minus c comes out when we take derivative with respect to t, minus cf2 prime x minus 0. This is supposed to be equal to given function g. This is the second boundary value condition, boundary value condition number 2. So we have these two equations. So the first one, remember, the first one says, maybe I erase this one to write it here. For the first one, we know that u of x and 0 should be equal to f of x for some given function, f. So we have these two equations. Any question here? Is it clear? Maybe it's, let's not call them boundary value. They are initial conditions. So let me change the way we call them. So initial condition number 1, initial condition number 2. We have these two equations. We can use these equations to find f1 and f2 explicitly. So let's rewrite these equations. So f1 of x plus f2 of x, f2 of x is equal to f of x, and c f1 prime of x minus c f2 prime of x is equal to g of x. So note that here, f of x and g of x are given. We know what these functions are. f1 of x and f2 of x are unknown. We want to find them. We want to see what are their values. We want to solve them, find them in terms of f and g. Is everything clear? Is everyone following? Any question? Okay. So multiply the, let's multiply the first equation by well, let's see. Yeah, let's multiply the first equation by the constant c, and let's integrate the second equation. So let's integrate with respect to x. We would have cf1 of x, let's say antiderivative, let's apply antiderivative to that, minus c2f2 of x. You know, it cancels the derivative. When we apply antiderivative, it would cancel these derivatives we have here. Would be equal to integral of gx dx. And then we would have a constant. This integral would be a function of x. Let's denote that with just capital Gx. Let's use capital Gx to denote this integral. So now we have two interesting equations. This is equation number 1 here. And this is equation number 2 here. Let's write them next to each other in the next page. So C f1 of x plus C f2 of x equals f of x. This is the equation number 1. Equation number 2, C f1 of x minus C f2 of x equals that integral, which we denote that with capital Gx, plus a constant a. Again, here, f of x is something we know. A is just a constant of integral, and g is integral of gx dx, which is also something we know. The unknowns for us are these two functions, which we are looking for. Well, simply we can add these two equations. We can look at their sum, right? So 2c f1 of x, f2 would cancel in the two equations. It would be equal to f of x plus gx plus a. And therefore, f1 of x is equal to f of x plus gx plus a over 2c. And then another time we can subtract these equations to find f2. So f2 of x would be equal to f of x minus gx minus a over 2c. So we have f1 and f2 here. Okay. Is there any question about these computations? Let me wait for a few seconds to make sure you catch up and make sure everything's clear to everyone. Okay, so there is a subtlety about the domain of these functions and the fact that we should extend them. I wouldn't go much into that, but remember, here the starting point was x was between 0 and a. Whenever it's necessary, when we are doing these techniques, we can extend every function to all of R periodically, right? So remember, whenever we have function defined on some region, for example, from 0 to a, you can periodically extend that. But there are different forms of extension. Sometimes you extend a function in an odd way. Sometimes you extend the function in even, in a form that the function would be an even function. This is what I want to talk about. We should extend these functions, this function here f and this function g. I want to tell you what sort of extension we need. So if there isn't any question, we can continue with this solution. No question? Okay, great. So so we have this function f of x and they have this function g of x, which both of them are defined on the interval from 0 to a to r. The idea is that whenever, as I said, we have this function, let's just draw something randomly from 0 to a, we can extend it. But remember, there are two types of extension. So if this is f, there is even extension, which I would repeat the function completely in a similar way in the positive side. On the negative side, I would look at its mirror. So it's even extension. We show that usually with f tilde with sub e, index e. There is another extension, which is an odd extension. We show that with f tilde o. So if f is defined originally here, we would repeat that. And here we would kind of mirror everything with respect to the origin. So we would reflect everything with respect to origin. So it becomes like that. And as you can see, these two things are different. Now the point here is that I want to extend these two functions to all of R. So their domain, I want it to be all of R. But first, we should decide what type of extension we want. Do we want even extension or odd extension? And then the solution would be defined everywhere in terms of the initial data. So so we had f1 of x. We solved this one. We saw this is equal to f of x plus gx plus a over 2. And we had f2 of x. It was f of x, 2c, sorry. It was f of x minus g of x minus a over 2c. Now, if we extend f and g to all of R, that automatically extends this function f1 and f2 to all of R too. Now it's defined everywhere. Okay. So great. So let's look at the function u. The function u at the point x and t was equal to, well, what was it? Let's look at the solution we got, the final solution we got. It was equal to this thing here. It was equal to f1 of x plus ct plus f2 of x minus ct. So let's write that down. f1 of x plus ct plus f2 of x minus ct. Now here you see why it's necessary to extend f1 and f2. although x was always between 0 and a, but we don't know where x plus ct is. You know, when you add, when time goes on, this x plus ct might go outside of this region. So if I write down the definition of f from here, I would get f of x plus ct plus g of x plus ct, you know, plus a over 2c. And plus, and then the same thing for f2. F of x minus ct minus g of x minus ct minus a over 2c. Now, the point here is that this x plus ct and x minus ct might not be inside the domain of these functions x, f, and g. So these things we should extend them to all of R, because t might be some very large number, right? So we should understand what type of extension we need. And this is not very hard to find out. So so consider the initial condition one more time. Now let's look at the boundary value condition. Boundary value condition was u at two endpoints 0 and t, and u at a and t are equal to 0. Right? When we have some string vibrating, these 2 points are fixed. Those 2 points don't move. Now, if we let x to be equal to 0 in this thing here, if we let x to be 0, here we have x, here we have x, here we have x, here we have x. Let's replace x with 0. Let's see what we are going to get. So we are going to see that f of ct plus g of ct plus a minus a, they would cancel each other, plus f of x minus ct. So if x is 0, we would get just f of minus ct plus g of x minus ct. Again, x is 0. We get this thing should be equal to 0. Sorry, the second one is minus. It's divided by 2c. We multiply the whole equation by 2c. Now, this equation is very interesting because we want our solution to work for any initial functions f and g. And remember, g was integral of g. So in other words, we want this thing to be always 0 for any f and g. So if I group these things, I would have f of ct plus f of minus ct plus g of ct minus g of minus ct is equal to 0. If we want this to be 0 for any given f and g, this should be 0, and also this should be 0, and then their sum would become 0. Let's call this one the equation number 1. Let's call this one the equation number 2. Let me rewrite the equations here. F of ct plus f of minus ct should be equal to 0. G of ct minus g of minus ct should be equal to 0. It tells us what type of extension we need, right? Call ct, let's show it with a new variable, anything. Let's call this s. It shows f of s should be minus f of minus s. And the second one shows us g of s should be equal to g of minus s. So it tells us that f should be odd. G should be even. So when we were thinking about what form of extension of f we should consider, for f, we should take the odd extension. For g, we should take the even extension. Right? And now just putting these even and odd extensions back into the equation, let's go back. This was the definition of u. Let me erase these extra things. And I told you this thing doesn't really make sense because f and g might not even be defined. we should consider their extension. Now it makes sense. We extend f and g. F is odd extension, G is even extension. F is odd extension, G is even extension. On the other hand, it doesn't matter what A is because this A here cancels with this other A here. So we get actually our final solution. Let's rewrite that. So U of X and T is equal to the odd extension of the given function f of x plus ct plus even extension of the integral of the given function g of x minus plus ct over 2c plus odd extension of f at x minus ct minus even extension of g at x minus ct over 2c. And that is the solution to the equation. Here, just to remember what parts we will have in the exam. So I know I'm a little bit over time, but let me just write it down so we all know. So from chapter, well, either you can follow the class and the lecture notes, or you can look at the book. From book, Chapter 0, ordinary differential equations, we looked at 0.1 and 0.2, homogeneous and non-homogeneous equation. Chapter 1, the Fourier series, we looked at 1.1, which was periodic functions. We looked at 1.2, which was about exactly these periodic functions. We looked at 1.3, which was about uniform convergence. It was about convergence of Fourier series, actually. We looked at 1.4, which was about pointwise and uniform convergence. We looked at 1.5. It was about operational Fourier series, adding two Fourier series together and things like that. We looked at 1.9. It was about Fourier integral. We looked at 1.10. There we learned about the complex Fourier series and Fourier integral. Chapter 2 was about the heat equation. 2.1 was about just writing down the equation. 2.2 was about the steady state. 2.3 was about 2.3, 2.4, and 2.5 and 2.6. Let me write them next to each other. They were just examples, which we solved all of them in the class. They were just examples, solved examples of the heat equation. 2.7, this from this chapter, it wasn't in the midterm. This is after midterm. 2.7 was about Sturm-Liouville problem. 2.10 was about semi-infinite bar, which we have it in the homework now. 2.11 was infinite bar from both sides. Again, we have it in the homework. Chapter 3 is the wave equation. 3.1 was writing down the wave equation. 3.2 was solving the wave equation using the product method. 3.3 is exactly what's studied right now. Just the solution we studied right now was chapter 3, section 3. We studied chapter 4. Chapter 4 is the potential equation. 4.1 is writing down the potential equation. 4.2 is solving the potential equation on a rectangle using the product method. Next week, I'm going to just solve more examples about potential equations. So if you look at the book 4.3, 4.4 and 4.5 are just examples. I'm not going to really teach anything new next week because, well, it's very close to exam. So I'm going to just solve these more examples about the potential equation. Okay, also, if anyone has not handed in any homework, you still have time, even if it's if it's late, I still would reduce some point, but you still can hand in your homework, and that would definitely help. So yeah, so that's it. The exam is on July 1st. It's during the class. It's again 6 p.m. So if you have questions about homework, I would stay around. You can ask. Is there any other question not related to homework? Yes, the exam would contain all of these things here. So these are the things you need to know for final. Yeah. Okay. Any other question? Okay, great. I wish you the best of luck. If you have any question, you can email me. We can manage a Zoom meeting. You can come to my office hours. And I hope you can read it and learn a lot and do well in the exam. We can stop the class here.